Alright, today we will talk about SVM Project and we will use Banknote Dataset. So here you can see our libraries and it is important, line 4 for SVM and other things, model selection, train test split and Matplotlib, Seaborn and Scikit-learn pipeline, and for warnings these two. And let's look at our code. Here in the function called load banknote data, we are pulling in the banknote authentication dataset from OpenML. That dataset contains numerical features that represent wavelet transformed images of banknotes, and the goal is to classify them as genuine or fake. After loading, we separate the data into X for the features and Y for the labels. And since the labels come in as strings, we make sure to convert them into integers, mapping 0 to genuine and 1 to fake. That way, the labels are ready for machine learning models that expect numerical inputs. So, now, once we have got the dataset, we need to evaluate the performance of our SVM model. That happens in the function called evaluate SVM model. And inside this function, the model first makes predictions on the training set and the test set. Then we calculate the accuracy for both. Accuracy is simply the number of correct predictions divided by the total number of predictions. And next, we run a 10-fold cross-validation on the training set. That means the training set is split into 10 parts. And the model is trained and tested 10 times, each time using a different part for testing. And this gives us a more reliable estimate of the model's performance instead of relying on just one split. And that's okay. So here the function also collects predicted probabilities on the test set, and these probabilities are needed to compute the ROC-AUC score. The ROC-AUC, which stands for Receiver Operating Characteristics Area Under the Curve, measures how well the model can separate the two classes across different thresholds. A score of 1 means perfect separation, and a score of 0.5 means the model is no better than random guessing. So, all these results, train accuracy, test accuracy, cross-validation mean, and standard deviation, ROC, AUC, predictions, and probabilities are packed into a dictionary and returned. And this makes it easy to use them later on for reporting and visualizations. So, let's continue. We will talk about the visualizations, which start in a function called create visualizations, and the goal of this function is to give us multiple ways to understand both the dataset and the model's performance. And let's continue. The first subplot shows feature distributions by class. For the first two features, we plot histograms for genuine and fake nodes separately. This lets us see whether the classes are separable based on their distributions. If one class consistently has higher or lower values, that's a sign the feature is useful. And let's continue. The second subplot is a correlation matrix. So here we calculate the correlations between all features and display them in a heat map. Correlations help us see if some features are strongly related. If two features are highly correlated, they might carry similar information. And the third subplot is box plot comparison. It shows the spread of each feature across the two classes. It's another way to see class separation and detect potential outliers. So, next in subplot 4, we plot a scatter plot of the first two features, coloring genuine nodes in blue and fake nodes in red. This helps us visually check if the classes are separable in two dimensions. Yes, and what is next? Subplot 5 is a confusion matrix. This heatmap shows where the model is making correct predictions and where it is making mistakes. The diagonal values are correct predictions, while off-diagonal values represent misclassifications. And subplot 6 is the ROC curve. It plots the true positive rate against the false positive rate across different probability thresholds. The diagonal dashed line represents random guessing, and the orange curve represents our model. The further the curve is above the diagonal, the better the model. Yes, and what is next? Subplot 7 shows the results from cross-validation. Each bar represents the accuracy for one fault, and the red dashed line shows the average accuracy across all faults. And this tells us how stable the model is across different subsets of the data. And let's continue. 8 is here. It is a learning curve, and this plot shows how accuracy changes as we increase the training set size. If the training and validation curves converge, that's a sign of a well-fit model. If there is a big gap, the model might be overfitting. And let's continue. 9 plot is here. It tries to show feature importance for the near kernels. SVMs give us coefficients that represent the contribution of each feature. We take the absolute values of those coefficients and plot them as horizontal bars. If the kernel is nonlinear, like RBF, we can't extract feature importance, so the plot simply tells us it is not available. Let's continue. After all the subplots are created, the layout is adjusted so everything fits nicely, and then the figure is shown. Here you can see. So let's move to the main function. Here we put everything together, or final part. First, we call the data loading function and split the dataset into training and test sets. We use stratification so that both sets have the same proportion of genuine and fake nodes. Okay, and next we define a pipeline. You can see here. This pipeline first applies standard scalar, which standardizes the features to have zero mean and unit variance. This step is especially important for SVMs because they are sensitive to feature scaling. Then the pipeline adds the SVM model with probability estimates enabled. So param_grid defines the hyperparameters we want to test during grid search. We vary the regularization parameter C, the kernel coefficient gamma, and the kernel type itself. So what is next? Grid search CV runs the search with 5-fold cross-validation and parallelizing the work across multiple processors for efficiency. And after fitting the grid search on the training data, we retrieve the best model. Okay, best model is here. So final parts here. With the best model in hand, we call our evaluation function. You can see here, and then print out the results. The best parameters: best cross-validation score, training accuracy, test accuracy, cross-validation mean, and standard deviation, and ROC AUC. And we also print a classification report which gives precision, recall, and F1 score for each class, as well as the confusion matrix again. Then we dig into the SVM details in this part, and what's happening here? We check that we check what kernel was chosen, how many support vectors were assigned to each class, the total number of support vectors, and the percentage of training points that ended up as support vectors. This percentage is interesting because a high number of support vectors can mean the model is more complex. And finally, we generate all the visualizations with the create visualization function and return both the model and the results. and if name part. So let's look at our output. First we will look at this, and yes. So outputs. The very first thing we see is the best hyperparameters chosen by the grid search. In this case, the optimal settings are C equal to 1, gamma set to scale, and the kernel is RBF. That means the radial basis function kernel worked best for this dataset. Right below that, the cross validation score is reported as 1.000. The training accuracy is also 1.000, and the test set accuracy matches exactly. The cross-validation mean and standard deviation show perfect stability, and the ROC-AUC score is again 1.000. What this tells us is that the model managed to separate the two classes perfectly, at least on this dataset. Next, we see the classification report for both classes, genuine and fake. The precision, recall, and F1 score are all exactly 1. Precision being 1 means every node predicted as fake really was fake, and every node predicted as genuine really was genuine. Recall being 1 means the model didn't miss any examples of either class, and the F1 score, which balances precision and recall, is also perfect. And the accuracy, macro average, and weighted average are all 1 as well, confirming that across the board the model made no mistakes. So if you look at the confusion matrix, it confirms this. We see a 2 by 2 grid. The top left value 122 represents genuine nodes that were correctly predicted as genuine. The bottom right value 153 represents fake nodes correctly predicted as fake. The off-diagonal values are 0, meaning there were no misclassifications. After that, we get some extra details about the support vectors. The kernel is RBF. The number of support vectors per class is 42 for genuine nodes and 44 for fake nodes, for a total of 86 support vectors. That works out to about 7.84% of the training data, and this tells us how many data points the SVM relied on to define the decision boundary. And let's turn to the visualizations. The histogram on the top left shows the distribution of two features colored separately for genuine and fake nodes. You can see that while there is some overlap, there are also clear areas where one class dominates, which makes them good predictors. The correlation matrix shows how features relate to one another. Some pairs, like the second and third feature, have a strong negative correlation of about -0.79. That means as one increases, the other tends to decrease. The box plot tells us compared spread of each feature by class. You can see that the medians and the ranges are different between genuine and fake nodes, especially for some features. Moving to the scatter plot here, when we look at the first two features plotted against each other, we can already see clusters forming. Genuine nodes tend to be grouped in certain regions, while fake nodes occupy others. And this visual separation hints at why the SVM is able to such a perfect job. Confusion matrix heat map again shows perfect classification. All the samples are on the diagonal 0, 0. The ROC curve is shown as an orange line sitting flat at the top left corner with an area under the curve of 1. This is ideal curve showing perfect separation. Yes, in the cross-validation bar chart, each vote achieved an accuracy of 1. The red dashed line showing the mean is also at 1. This tells us the model's performance is not just perfect on one split, but consistent across all 10 folds. The learning curve plot shows both the training and validation scores pinned at 1. There is no gap, meaning the model generalized perfectly from the training data to unseen data. Finally, the feature importance panel is blank except for the note that importance is not available for the RBF kernel. And that's because nonlinear kernels don't give us straightforward coefficients to interpret. So when we step back and look at everything together, the matrix, the confusion matrix, the ROC curve, the learning curve, it is clear that this dataset is perfectly separable by an RBF SVM. Every evaluation metric is at the maximum, and every visualization supports the idea that the classes are well structured for this type of model. And that's for this SVM project, and thank you for listening.